Here we are. Today is our last lecture of the winter 2020 semester. We're going to do a little bit of final exam review, get everybody prepped for the exam, and then grind this thing out. We're just about done. It's been a long, strange trip. We're just about done. So, in order to make accommodations for people who at this point are all over the world after leaving campus to go home, we've adjusted the offerings of the final exam. There's going to be 3 final exams offered. One at the normal slot given to us by the registrar's office, which is about 8 a.m. Ann Arbor time. And then for the next 24 hours, every 8 hours, we're going to have another exam. So there's one around 8 a.m., there's one around 4 p.m., and there's one that starts at midnight of Tuesday, Ann Arbor time. So all these times are Ann Arbor times, and we will have a chance to get everybody assigned to an exam because of the way that the software we're using is working. We have to know where you're going to be, which sitting you're going to be in, and then you can only take the exam during that seating. So 7:50 a.m., 3:50 p.m., and 11:50 p.m., all Ann Arbor times, Monday, April 27th is when your exam will begin. We're going to give you 2 hours and 20 minutes. This is to sort of hopefully combat any sort of technology issues that may crop up, slow connections or whatnot. So it's going to be a little bit of extra time there while still making sure that we're done early enough for anyone who's got a 10:30 exam later that morning. So the accommodation exams for people with extended time, those will start at any one of those original times and then just travel an additional hour or 2 hours if you've got the 2x slot. So the time slots will be chosen via Google form. I've already sent that out. You should have answered that. It was very insistent that you do, because if you do not answer it, then you will not be placed into a seating for the exam and you will not be able to take the exam. So you do have to do that. We are set to have closed that at midnight last night. However, I know personally that it's still open. So we'll leave that open through the end of lecture and through the end of the night. But once midnight comes tonight, we will close that form down. If you have not already picked a time to take the exam, you will be out in the cold, as it were. So make sure you get that done, and then we will get a confirmation email out to everyone to let you know for sure that we know where you are and to let you know when we think you are. So if we have a disagreement, then we can get that resolved before exam time. The policies for this exam have changed a little bit. Obviously, we're at home. We're now full open book, full open notes. You are not supposed to use external websites or additional tools, compiler, anything like that. Just what you got upstairs. And of course, a cheat sheet. Cheat sheet is still useful even with open book and notes. Having a cheat sheet is good because it's boiled down all of the things that you think are important. It's focused your mind on getting them written. We really, really like handwritten cheat sheets for the reasons that we talked about during the midterm exam. The handwritten cheat sheet is going to put it in your mind better than a typewritten cheat sheet or something that you may copy and shrink and make smaller. So we're not monitoring this, obviously, so you can have as many sheets as you want, but focusing all of your thoughts on getting this all into one good sheet is a great way to be prepped for this exam. So please try to do that. That is our best suggestion there. Handwritten makes you learn it better, lets you know on the sheet where it is. So when you're stressed during the exam, you're trying to find something. If you just sort of typed this stuff or copied it down and shrank it or whatever, or just are flipping through all of your pages and pages of notes, it's much harder than if you have written this down in the last 24, 48, 72 hours and you know exactly where it is, you go there. So we would strongly suggest you still do write out a cheat sheet with all of the things that you need for this final exam. Engineering honor code, of course, still applies. You have to do your own work, and we're asking that you do this well. Some other suggestions that we have is figure out the best way for you to work on the exam in terms of how am I going to be filling this out? Am I going to be editing a PDF because I can do that with a tablet or on a Mac, or do I need to do something else like printing this stuff out and scanning it and uploading it there? So please do have a pad of paper and a pencil handy so that you can have a backup plan in case something goes wrong, your technology fails, you can't get a PDF uploaded. You might be printing this out, you might be editing it on digital. Whatever it is, take some time, run through the practice exam. Make sure that you can do this exactly the way you plan to do it Monday morning. The multiple choice portion at this point is still 24 questions, 2.5 points each. That gives you 60 points, 60% of the final exam grade. There's going to be 4 to 5 possible answers per question. The majority of them are 5, some of them are 4. There's no deduction for getting the wrong answer, so make sure you answer every question. A blank answer is a definite wrong answer, whereas anything you write in there does have the chance of being a right answer, as long as you've only bubbled one thing. Never bubble more than one thing. Never bubble 0, never bubble more than 1, just 1. There's a Monty Python reference in there. I'll leave it to you. Study materials, of course, are the practice exams I just mentioned. Those are posted on Canvas. After this lecture finishes, the answer keys to those exams will be posted, so you will have had a chance to look at this and then also get some review and go after finding some answers. Lecture slides and recordings should be helpful, as well as the in-class exercises we worked on and things that you worked on in lab. As well, if you've got a study group, study groups are great. Even those that adhere to social distancing models, they're still great things to have. So another thing to do is you can look at programming interview questions. Those are a lot of the things that show up. We know for sure that one of the written problems is going to be a dynamic programming problem. So a great place to go there is just go to LeetCode. They've got a really nice tutorial on DP, and you can look through DP, and they've even got, I think, probably the top 20 common DP problems. Not saying that you're going to find one of those problems on this exam, but many DP problems borrow from each other. So the practice of getting to see a DP problem and then its solution is going to help you be prepared for this exam. So my suggestion personally is to study as many DP problems and solutions as you can. And not like deep study, but if you've got a couple of extra hours between now and then, and you got a chance to look at 10 DP problems and say, hey, I feel a little bit better about dynamic programming, then you're going to go into the exam more relaxed and more prepared. The exam is cumulative in the sense that you might be asked something that is supported by knowledge in the first half. There are no questions that are directed at lecture material from before the midterm exam. All of the questions are directed at lecture material after the midterm exam, with the exception of the strings and sequences lecture, which is going to be, which was given before the midterm, but wasn't asked on the midterm. It is now fair game for the final exam. Trees, of course, we've done plenty there with just general tree rules, binary trees, AVL trees in particular, searching, traversals. We'll look at hashing and collision resolution, graphs and some of the graph algorithms that we've dealt with. Definitely have to look into the algorithm families. We're going to go all the way through shortest paths. We're not going to include the Floyd-Warshall algorithm. Computational geometry is not included as well. It's a fun topic, but it's really hard to make good questions on CompGeo. So it's just good information to know for the future. All right, so summary stuff. Excuse me. We've got trees. Wonderful picture of a tree here. General trees, binary trees, BSTs, and then our self-balancing binary search trees. AVL trees are the ones that we studied here in 281. First exercise, do something like this. Insert these keys into an AVL tree, rebalancing when necessary. So it's at this point during the final exam review, during any exam review, I like to give students encouragement about how to succeed at an exam. The material that you've covered while you're studying, while you've watched lectures, your goal is to be able to show that you understand it. Obviously, you want to understand it, but for the exam, you need to show me that you understand it. So as you look at a question like this, an exam studying exercise, say, I'm going to insert some things into an AVL tree. You should be approaching this with the thought, how am I going to be asked to show that I understand this stuff? So here's a perfectly good exercise. Maybe I would have to draw the resultant tree. I'm not going to rule that out. In the past, that has been a question. We had to draw a tree there, and we actually corrected visually drawn trees. Another way to do it is, how could I turn something like this into a multiple choice question? How can I take something and figure out a multiple choice way to test whether I can do AVL tree insertions? We know that after some insertions, rebalances are required. The rotation, the fixed things. So one way to do that is I could say, well, after inserting these values into an AVL tree, how many times did you rotate? Another multiple choice style question was like, what is the left child of the node 8? It could be empty, it could be 7, it could be 5, it could be 3. There could be a red herring in there, like the left child of 8. Is it 13? We know that would never work in a BST, but those are the kind of things that happen on exams when you're trying to prove that you understand how to do a particular thing. And so in this case, inserting into an AVL tree. So go through these topics as you study them, and it's going to be a bit more straightforward than it was in the midterm to understand this material. The material is just less abstract and much more concrete. So as you're going through this stuff, it's going to be fairly easy to read something and say, oh yeah, I wrote a piece of code on that in Project 4, or I wrote a piece of code on that in Project 3. I really do understand it. Or even if I didn't write something in a project, I did something in a lab and I understand it. But you need to be asking yourself, how are they going to ask me a question that gives me a chance to prove that I understand it? Okay, so think about those things as you go through here. So we've got our first exercise. We're going to try to insert some items into an AVL tree. We've done something like this in lecture. So we're going to start out with these insertions, and I'll just put the values up here: 4, 2, 3, 5, 7, 8, 9, 13, 12, 10. 13, 12, 10. All right, so for insertion, I'm going to start out with 4. Less than that is 2. And after inserting 4, 2, and 3, this is what my AVL tree looks like. It's clearly out of balance. I've got a left height of the root at 2 and a right height at 0. So I'm going to plus 2. But as I travel down from 2, you see that, as I travel down from 4, you see that this plus 2 imbalance is trailed by a -1 imbalance that's going on, the -1 balance factor on the node at 2. So this is going to be a zigzag, and you can see the zigzag quite plainly here. But the zigzag is going to be fixed by a double rotation, which is first going to be a rotate left around 2, followed by a rotate right around 4. So rotate left ends up with something that looks like 4, 3, 2. And then the rotate right is going to bring me up to a 3 at the root with 2 and 4 looking something like that. All right, next insertion is a 5 that fits, followed by a 7. Now I've got a couple of places where my tree is out of balance. 4 has a balance factor of -2, 0 height on the left, 2 height on the right. 3 has a balance factor of -2, 1 height on the left, and a 3 height on the right. But we're going to work our way up from the insertion point, which is from the bottom up. We inserted the 7 most recently. As we move up from 7, we see that 7 is obviously balanced. It's a leaf node. 5 is balanced because it's got a balance factor of a -1. And then the 4 is the first place that I find my imbalance. So I'm going to correct that imbalance before I try to work any farther up my tree here. So fixing that's going to be straightforward. It's just going to be a rotate left around 4, right? And I'll end up with something that looks like 3 with 2 on the left, 5 on the right, children 4 and 7. So that tree is done. That single rotation has fixed our imbalance, and now we are completely balanced. I got to do some more insertions, and I'm going to run out of space here. So 8, that's not an insertion, 7 and 8. 8 looks like things are going well. It's obviously a leaf node, it's balanced. Its parent 7, it's got a balance factor of -1, that's balanced. Its grandparent 5 has got a balance factor of -1, it's balanced. But the great grandparent there, up there at 3, has a left height of 1 and a right height of 3. So our -2 balance factor still remains on this 3 node. Well, it has been recreated after this last insertion. So we'll fix this with just a simple rotation left around 3, which sends 3 down and pulls 5 up. That's the heart of the rotation, is to swap a child-parent relationship. So 3 was the parent, 5 was a child. After the rotation, 3 is the child, 5 is the parent. 3 brings with it, of course, its own child. And 5 has a child now that it no longer has room for. It previously had a left subtree that began with that 4 node, but since it's going to put 3 on the left subtree, we've got to pass that left subtree over here to be the right child of the left child. So that 4 comes in here, and then 5 brings up 7 and 8, and we're perfectly well balanced. Bringing in 9 sets up another internal imbalance. I've got a -2 here surrounding this 7, so let's rotate left around 7 again. Right, 7 is just going to go down, bringing 8 up, and 9 will look like that, and we'll end up connecting that back in here like that. So our drawing after that insertion is going to look like 5 over 3 and 2 and 4, with 8 here and 7 and 9 there. All right, so this is now complete. If we remember what a complete tree is, right? I've worked my way so that every level is full from left to right. This is also proper. If we want to talk about our binary search tree properties, this is a proper binary tree because every node that has children has exactly 2 children. So this is complete and proper and binary. All right. Next insertion is 13, which doesn't cause us any problems. And that's followed by 12, which gives us another imbalance, a set of imbalances really, right? Because I've got a balance factor here of +1, I've got a balance factor here of -2. So the 9 is out of balance, and you see that there's a zigzag underneath there because of the sign change. 9's got a negative imbalance, and its child that causes the imbalance has a positive balance factor. So we're going to have to get the double rotation to fix that there. As I continue to work my way up, I see that there's a -2 balance here. I'm not going to do anything about that, though, because when I fix the 9, it's actually going to fix the 8 as well. We've got a -2 balance factor here at the root as well. Left subtree height 2, right subtree height 4. So we'll fix this all with first a rotate right around 13, followed by a rotate left around 9. All right, so right around the 13 is going to make it look something like 9, 12, 13. That's good. Now it's no longer zigzagging. And then the left around 9 brings a 12 up and sends a 13 down. All right, so I'll get some more space over here and draw what that looks like. All right, we'll end up with a 5 at the root. No changes there. I've changed color, however. Got a 5 at the root, left to 3, 2, and 4. to the right. I'm going to keep that 8 in the position that it was in. And that's going to go left to a 7 child. And then we'll bring up 12 here with 9 and 13 below it. Sound good? Get some clarification here. 9 and 13 below it. So that's what it looks like after the 13 insertion. After the 12 insertion, sorry, let's rotated that back up. Last but not least, we have to insert 10, which is going to travel ourselves away down to the bottom of the tree once again. Clean. So checking my balance factors from the bottom to the top. Remember that every time I've got a leaf node, since it has no children, it's got a balance factor of 0. That's good. There's a -1 balance factor at the 9. There's a minus is a +1 there. It's got a 0 balance, 0 balance. This is a leaf node, 7 is, so it's got a 0 balance. 8, however, has a left height 1, right height 3, so it's got a -2 balance. Right there is going to be my problem. As I work my way through where this -2 imbalance came from, I see that I've got a +1 there. So once again, I've got a zigzag. My first repair is going to be fixing the +1 balance by rotating that to the right. So I'll start out by rotating right around 12, followed by rotating left around 8. After I'm done with that, my tree should be in good shape. So let's look at this rotate right around 12. That means I'm going to take its left child, promote it up to the parent, and drop 12 down to the new parent slot. So down below the 12, the 9 will come up, the 12 will go down. We'll have that. The 13 will remain below the 12. And the 10 now has to come up, which should be a right child of 9, but that's where 12 is. So we'll pitch that 10 as the right child of 9 off to be the left child of 12. So here's sort of like our intermediate step after the first rotation of correcting the zigzag. 9, 12, then over 10 and 13. Now as I rotate left around 8, 8's going to go down and 9's going to come up. Looking something like that. Did I get this right? Yep. Below 9, we've got 12, of course, 10, and 13. What happened with 8? 8 brings it 7. That's already there. Below the 5, we've got 3, 2, and 4. And there is our entire AVL tree constructed. We see that everywhere we look, we've got a balanced tree. And our binary search tree property holds. And there we have it. So remember, a binary search tree is just a binary tree, but it has a binary search tree property, which says that we've got some ordering from our left and right child. So the left child is going to be less than or equal to the root, and the right subtree is going to be greater than or equal to the root, depending on how you define that particular tree. In 281, of course, we like to use less, like the STL. So things to the left are less, and things to the right are not so less. Right? So that means greater than or equal to. However, it's worth noting as well that when you're working in an AVL tree and you start doing rotations, you can definitely lose that greater than or equal to on one side and less than on the other side. So the items will still be findable. You would find a parent one first before you would find them one that was on the wrong side below it, the quote-unquote wrong side. So that's something to be aware of. Moving from trees into hashing, we remember that hashing, we looked at hash functions. We looked at how hash tables could be created, and we looked at a couple of different mechanisms there. Then we looked at collision resolution, and that was divided into 2 separate ways as well. In collision resolution, we used separate chaining. That was one particular way to handle an overloaded hash location. And the other way to do it was through probing, where probing, linear probing, quadratic probing, and even double hashing, they all fell together under this umbrella of what we called open addressing. So rather than creating a new place to put things, which separate chaining does, when we run out of space, we just add more room in a separate chaining. In open addressing, we use a fixed size table, and when a particular location is already in use, then we just use some math to find a new open address. In linear probing, we're of course going to move just one spot farther and one spot farther and one spot farther until we find something. Quadratic probing, we move by jumping a little bit farther every time. We square the distance. And then double hashing, we use a secondary function to figure out how often or how far we move away from any particular value. So that's hashing. You come up with questions like this. What is the complexity of inserting into a hash table with m slots that stores n unique keys? It's a great review question. When we're using separate chaining, what's the best, worst, and average cases of complexity, right? Complexity of inserting into a hash table, m slots, n keys. Linear probing, what's its best, worst, and average? Well, for separate chaining, our best case insertion is constant time. We go to put something there, there's nothing there, it's an empty chain, easy peasy. Stick it in constant time. In the worst case, we've got separate chaining, but all n items have somehow, through some sort of bad luck, all ended up in the same chain. So in order for me to figure out if the value that I'm inserting isn't already in the table, I have to look through all of the items in that chain. And in the worst case, all n of them are in the chain, and so that's where I get that big O of n for worst case on separate chaining. Average case, however, in separate chaining says if I've got n items inserted into a table of size m, there's n divided by m items in each one of those chains. So that's where I end up with this big O of n over m, and when I've got the chance, I'm going to choose m to be somewhere as close to n as possible. So then we say that big O of n over m, we would hope to be average about 1. So n over m is a constant time thing when we can control things well. How about linear probing? Best case, of course, you go there, it's ready to go. That's an easy to see, that's constant time there. In the worst case, with linear probing, I've got a bunch of keys already inserted into a table, and I've got so many keys that I've got this cluster of keys next to each other. Every address that I would go to look at is full. Even if I were to control how many items I allowed to go into the table. So that was the thing that we worked on in the lab, was to say that we would like to rehash and grow once we got to an alpha or a fill factor of about 50%. Even if the thing was 50% full though, so I had a hash table that had 100 spots in it, that had 50 items in it, and I had used linear probing and they were all in one big cluster, you could see how all 50 of them next to each other could turn into looking through 50 items to find the next open spot. And with 50 items being chosen as a number, it seems a little bit more constant, but that value 50 was half of the size of the 100. So really you don't think of that as 50, it's more like m over 2. So if I've got to go through a cluster of size m over 2, that's a linear search, m over 2 items, which in terms of big O, that's big O of m, right? Or in this case, big O of n, really. I guess we're talking about looking at every item in the cluster, even if that cluster is half the size of the table. So the average is a much more complicated thing to figure out. We looked at that with the yellow line tables and some equations that we told you would not be on the exam. We put them up there for qualitative feel, not for you to have to deal with them quantitatively on the exam. So you can look to that in later stages of your future when you need to know exactly what's going on in average time For now, you just need to have a good feel for how that's going to work in average case. Question here was of uniqueness of keys here. A lot of times when we're using a key in a hash table, if I set something at some key equal to a value, and then later I set something at that key to a different value, I generally mean to overwrite that value. There are some containers that allow you to have multiple keys, of the same value in the table, but that's a different approach to what's going on there. Second question was, why doesn't linear probing worst case come out to be big O of M if we have a table full of deleted ghost keys? In this particular case, big O of M and big O of N are not really that different, right? In the terms of linear probing, we saw from when we were doing the actual formulas for timing on that, we saw that we used those yellow line tables, and we said getting to something that was half full was about as bad as we wanted to get. So in that sense, linear probing would never let you get to more than M over 2 of the items. But since you were looking through all N of them, even if you decided to take a table and say, well, I don't have that much memory, I'm more memory constrained, and I would rather use, I'd rather have to pay the time for it, maybe I'll let my table fill up to 75%. That value that you're looking at, 0.75 M, those are the things that I have to look through. 0.75 M, as I look at big O of that, is going to be a big O of M. But it's also, as I look through each one of the things that I've inserted, it's a big O of N. So that's what I'm saying. In this particular example, the worst case and best, the worst case is big O of N, and it's also big O of M. But more importantly, you could go with the worst case with fewer than the thing being full. So in the worst case, I could have a table that's got 1,000 items in it, and if the 20 of them that I have are all in one cluster, the worst case is I try to insert at the beginning of that cluster, and I have to look through all 20 of the items that I've already inserted. So it's still a linear search in the total number of items I have, regardless of the fact that the size that I have, the capacity that I have available to me, is even larger than that. So that's why we don't focus on it being a big O of M. We focus on it being a big O of N, because you're only trying to deal with the items that you've created, not so much the size that's controlled by the container itself. And finally, our last bulleted point here, search complexity is, of course, the same as insert. I've got to do many of the same things. I've got to find whether or not this thing exists, or find whether or not space exists for it. And those take me about the same amount of time. So search complexity, same as insertion complexity. Next major topic, we're talking about graphs. Wonderful graph of the internet here. It's a pictorial version of it. Go look that one up. So we have some things to discuss in graphs in general. We have lots of terminology. It's a lot of sort of binary things that we talked about in terms of the terminology. There was adjacency matrix versus adjacency list. There was sparse versus dense. There was directed, there was undirected. There was weighted, there was unweighted. We looked at graphs this way. So there's a lot of terminology that we had to pull off there. We looked at some search mechanisms for graphs. We slipped one in on you. Project 1 was a breadth first search, depth first search. Even though we hadn't talked about graphs at the time, we gave you a graph and an algorithm, and you did a breadth first or depth first search. Other things we did with graph was tracking down MSTs. We had to do a prim for a project. We did not end up working on Kruskal's, but we hope that you do understand it. Kruskal's is going to be a similarly greedy algorithm. Prim and Kruskal's both greedy algorithms to finding an MST. And then the shortest path algorithm, which we did look at, Dijkstra's shortest path algorithm. We talked about a way to apply Dijkstra multiple times to get the all pairs shortest path, but we only need to go through this exam a single source shortest path. So those are the things we'll look at. Here's our slide with terminology. We had edges, Those are the connectors between two locations on the graph, and those are called vertexes or nodes. Both are legal. It's also legal to call those vertices, so you'll see that a bunch of different ways in the literature. Node, nodes, vertex, vertexes, vertices, they're all right. The degree talks about how many connections come out of any particular node. The weight and unweighted, we talked about how those things modified edges, directed, undirected. We looked at simple graphs with no parallel edges and no loops. We looked at a couple of different ways to store this. Sparse and dense. So these are all the terminology that you should know and understand as a starting point for where you're studying for the graphs here. Then we did, of course, some heavy-duty work dealing with Hamiltonian cycles. You should definitely be able to manage that. The graph problems we looked at, traveling salesperson, that was project 4. Graph coloring we did only in slides, I believe. We looked at knapsack as well in lecture, and we had a nice demo on nQueens with some code that you can look up on Canvas. So here is a place where we can get started. How about Prim's algorithm and Kruskal's algorithm on this graph, with the caveat that we should start at A. All right. Prim's and Kruskal's, I feel like everyone in the course that's made it this far has worked with Prim's algorithm. It was a major part of Project 4, and if you're thinking you're going to sit for the exam in an attempt to pass this class, I would have hoped that you've gotten something done on Project 4. So we'll skip doing this with Prim's. I'm going to imagine that you can find a way to get this done with Prim's algorithm. I'll just illustrate how I might do this with Kruskal's algorithm. All right, so in Kruskal's algorithm, I've got to do 2 things, right? The first thing I need to do is get a collection of all the edges and get those edges sorted by weight. So I'll take CF for 1. I'm just going to do a visual sort as I write them down, because humans can do these things much better than machines at this scale. FG for a pair. Moving forward, I've got AB for 4. EF at 5. EG at 6. Make sure I don't skip anything. Got DE at 7. AC at 8. And BD at 8. So you can see right away there, that's where I'm going to have a choice in the future to these values that come in with the exact same weight. And it doesn't matter what order I put them in. In this case, I've chosen to sort them alphabetically by their vertexes. But I could have done this the other way. I could have put BD earlier in the sort than AC. And I would still come up with an MST. I might come up with a different MST, but it would be one that had an equal weight. So that's okay. Remember that MSTs are not necessarily unique per graph. I just need something that is optimal, right? Something that's minimal, and there might be multiple different ways to achieve that same weight. Few more edges remaining here. I've got BC for 9 and DF for another 9, followed by BE for 10. So let's count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. And it looks like I should have 12 edges. Okay, so step 1 is collect all the edges, sort them. The next thing I'm going to do is just start growing a collection of trees until all of the trees have merged into one. And to do this, I need union find to help me out, because I want to make sure that I don't connect anything with more edges than I need. All right. So to do union find, the easy way to do that is to give myself a table of each one of these values and figure out who their representative is. Got A, B, C, D, E, F, G, and I'm going to set each one of them to be representing themselves. So that will let me know when I pull an edge out of my sorted container if I can add that edge to the graph. All right. So for starters, we'll go here with CF. And CF with a weight of 1 it looks like C's representative is C, F's representative is F. I can include that edge in my graph. So I'll take CF here, and the way I'm going to update my union find table, I'm going to take the early vertex and update the late vertex, right? So C's representative is C, F's representative is now C. All right, next edge coming out, C and D. Well, C's representative is C, D's representative is D, so that's an edge that I can also include. And that lets me fill this in right here. I'll change D's representative to C and move on. Next up, F and G. F's representative is C. G's representative is G. They're two separate values. I'm going to say that can be included. All right, so I'll change G's representative to be the earlier vertex's representative. F's representative was C, so we'll change that right there to be C. So now we've updated that. And let's draw this edge in. That's good. Next up, A, B. A, B, A's representative is A, B's representative is B. That's an edge I can include, right? And so here's where we differ from Prim's algorithm. You see now I've got two separate trees. They aren't connected yet. But I can mark that edge as something that I was able to include. And I'm going to change B's representative to be A. And then I move on. How about EF? E's representative is E, F's representative is C. They are two separate values. I'm going to say that they can be joined. E and F here goes along there. And E's representative is E. So now as I update F's representative, right, that means I have to update C to be represented by E. So if I change that here, you see that now I've got everyone not necessarily their own representative. They might not even know who their representative is, but they will know someone who knows who their representative is, right? Because you see the chain of F going through C to E. So there is a place where the next time I do a find on F to find out who F's representative is, if I'm using path compression, I'll see that F's represented by what it thinks is C, but C says, no, really we're represented by E. So then with the path compression of finding, by the time I get done with that, E should be representing C, E should be representing E, and because we originally asked through F, E will also be the direct representative of F. So that's how path compression works, and I'll see that on my next find through F, right? Next up, E and G. Looking at the graph, you can see that that makes a cycle, so that's not going to be allowed. But then as we go over and ask the union find table, I see that E's representative is E, G's representative is C, but C's representative is actually E. So that find there would change this with path compression to say that G should really be represented by E, because ultimately that's the way that it is. And since G is represented by E and E is represented by E, they cannot make that an edge in this graph. So that one is not included. The same goes for DE as well as I try to insert the next edge, right? I see D's representative is C, C's representative is E, so through path compression, I'm going to change D's representative right away to be E. And since E's representative is E, they're the same, I cannot include that edge either. But path compression has made me not have to look up D to C to E any longer. The next time I need to ask something about D, it's going to be able to go straight to its representative, E. All right. And I'll answer that one in a moment. Let's finish this up here. A to C, that's my next insertion. A's representative is A, C's representative is E, and E is the ultimate representative, so I don't need to update C because it already knows who its ultimate representative is. But A's representative is A and C's representative is E means they are different, and that means I can include this edge here from AC. Now, if I'm paying attention, I note that I have 7 vertices and I have inserted 6 edges, so an adaptive version of this would stop now. There's no more work to be done. All I will do as I look up BD and BC and DF and BE is find out that those edges are just creating cycles, and so I cannot insert them. All right, so this is my final version of this. You see, this is the answer slide here, and we've got a dotted line on this BD because I could remove the AC edge for 8 and insert the BD edge for that same 8 and come up with a different but equivalent MST. All right, so one question that we had in office hours today was talking about how these greedy algorithms work and how do we know that greedy algorithms work. And both Prims and Kruskal's are greedy algorithms. And because a greedy algorithm works by taking a locally optimal choice or a collection of locally optimal choices and hoping in the end that we end up with something that is globally optimal, that's how greedy algorithms work. And in this case, with both Prims and Kruskal's, because taking a small edge early sort of removes an edge of that size off the board. There can never be anything shorter than an edge that you've selected. So the greedy optimality principle is basically stating that a greedy algorithm is optimal if for every decision I make, it doesn't prevent me from making some better decision in the future. So if I was trying to make change for 40 cents and I had a quarters and I had 20-cent coins, 5-cent coins, and 10-cent coins, I would go the 25 and the greedy, and then I would have to take the dime and the nickel to end up with 3 cents. Whereas if I were to say, well, let's not take the best now, let's not take the 25 now, because if I take a slightly worse choice now, I'll end up with a better result. That's not a greedy algorithm, right? That doesn't give me the chance to. Or if I choose the 25 like I should in the greedy algorithm, it rules out me being able to choose 2 20s later on and get to an optimal solution. In Prims or Kruskal's, the way that they work is they work by taking the shortest edge available, right? Prims takes the shortest edge that's connected to anything that we currently have in the tree. Kruskal's takes the globally shortest edge. But in either of those cases, taking the shortest remaining edge doesn't prevent you from taking something even shorter than that later by definition, because we've taken the shortest remaining edge. There's no way that we can come up against the choice or not be able to make the choice of something shorter in the future. So yes, both Prims and Kruskal's are optimal at all times. They're both greedy, and yeah, that's how it works. Here's Prim's algorithm in pseudocode. You'll remember this from slides. You'll remember this from P4. I won't go too deep into it. We did the version of it because we were working with a dense graph. We did the version where we used the 2-loop or the multiple loop, the nested loop version. So that ended up being V squared. If I had a sparse graph, Kruskal's is edge heavy. It looks at edges more than it looks at vertices. So we get all of those edges and we sort them, and so that's where our sort takes place. And so with a sparse graph, we would probably use Kruskal's, but if we were to use Prims, we wouldn't have to do the linear search of looking at everything in the row. I would end up with these heaps, and I could push just one heap. I would push the edges that were connecting a particular vertex into a heap, and then I would be for searching. Kruskal's algorithm is greedy, of course. It's an MST algorithm for edge-weighted connected undirected graph. First, we have to pre-sort all the edges. So that's edge in a sparse graph, where E is on the order of V, right? In a dense graph, E is on the order of V squared, and so we wouldn't want to do something like that here for Kruskal's. So E log E is usually written up as E log V. So we have to pre-sort all the edges, which you saw me do just by inspection. I didn't spend the computational time. I just looked at it and did it. When you're writing software, of course, you've got to write that sort in there. Then you try inserting them increasing order of weight using our union find to prevent cycles, and we discard edges that create cycles, and then once we've got enough edges to get an MST, we call it done. The initial 2 edges, or the initial, you can have many. If I've got a graph with thousands of points, I might have, hundreds or maybe even thousands of individual groupings of just these two items. Maybe you're only connected to the closest item to you, and then there's 500 different things that are all connected to just one item. So the initial two edges may be disjoint. It should be more correctly like many disjoint subtrees will eventually be pulled together. So it's not necessarily growing a tree like we did in Prim's algorithm. We're really growing a forest that eventually grows dense enough till it feels like a single tree. It isn't a single tree, yeah. Dijkstras algorithm. This was a greedy algorithm that we used for shortest path. You can assume non-negative weights, of course. That's part of how the shortest path algorithm works. You need to find the shortest path from V sub s to every other vertex. And this ended up being based on Prim's algorithm. So it looks a lot like Prim's algorithm. We had this K, D, and P. K sub V is the shortest path from the start to this vertex known. D sub V, what is the distance from the start vertex to this vertex? And P sub V, what is the vertex that precedes this vertex on the path between vertex V sub s to here. So KDP was what we used in Prim's, and we made a slight modification to Prim's algorithm. So instead of just taking the shortest distance from some vertex to one of its neighbors, we added that distance to the source cost, getting from the source algorithm to that vertex originally, and then adding that to the distance to each of its neighbors. And that table ended up working just about the same. So starting here, let's see if we can't pull off a Dijkstras here on this particular graph. And if you look at it, we can do this one by inspection ourselves. We're going to include the 1 and 2 edges. So just by inspection, you see that should be in, that should be in, that should be in. The next shortest edge, the 4 should be in. We remember we did a proof that said I can insert these edges as long as they don't cause me cycles, remember? So, oh, wait a minute, I'm doing Prim's again, sorry. I should be working on shortest path. So finding the shortest path from A to G, right? So do Dijkstras algorithm starting at A. I can figure out what that is by inspection here. I think I can cut across and go 4 to 8. Yeah, all right, let's just do Dijkstras. So another question here. How do I show on the exam that I know how to do Dijkstras? Right? Dijkstras is the shortest path algorithm. And given this question in an exam, if I were to ask you, what's the shortest path from A to G? Without knowing how to do Dijkstras and an additional 2 or 3 minutes, I could just find every possible path from A to G, figure out which one was the least, and then that would be my answer. That wouldn't show that I know how to do Dijkstras. So how might a question like this come up in an exam that shows you know how to do Dijkstras? Dijkstras is an algorithm. It's a process. So question that's going to test whether or not you understand Dijkstras is going to be looking at how you implement that process, or when that process is being implemented, whether or not you understand which step should be next or how steps should be done. So you could say, if I were to do Dijkstras on this graph, what order would the nodes be marked as known? That's one way to do it. In multiple choice questions, you could say, which vertex was marked true right before F? Was it A? Was it B? Was it C? Was it D? Was it E? Or was it none of the above? So those are the kind of things that you should be looking at as you're studying. Is like, how can I prove that I know this? How are they going to test that I know this in a way that isn't easy for me to just come up with the answer whether I know this method or not? So to manage Dijkstras here, I'm going to have to get myself a KDP table, of course, KDP, and I'll put my values in there, A, B, C, let's go D, E, F, and G. All right, so there's my nodes, and if I start out and say that the distance to A is, of course, 0, then I'll go through and mark this thing up pretty decently, right? So I'll mark that one as true, find all of the things A is adjacent to, add this source cost of 0 to both 4 and 8, and end up with the fact that I've got a distance of 0 plus 4, 0 plus 8 there, both parented by A. Sorry, I changed my letter case. Next step, I find the next shortest faults. That's going to be this B. I find the things adjacent to B, but I have to add this source cost of 4 to them. So the B to C cost is not just 9, it's 9 plus 4, or 13, which is not an improvement over the C that I have, so I'm going to leave that one alone. B to D cost is 8 plus the source cost of 4 gives me a 12 distance to D, which is an improvement over infinity through B. And it also gives me 4 plus 10, or 14, to get to E through B, which is an improvement over infinity. That iteration complete, I find my next closest faults. That's going to be C with a source cost of 8. So I'll add that to every edge that C gets me. A and B are already marked as true, so I don't need to check them. C is still adjacent to D and F. So I can add 8 and 2 to get to D and 10, which is an improvement. So we'll change that to a 10 and say I would get there through C. And 8 plus 1 to F is a 9, and that's an improvement over infinity as well. So that iteration complete. I find my next closest faults, which in this case now is F. So I'll mark that true and adjust its neighbors. F is adjacent to C, D, E, and G. C is already marked as true, so I can get to D in F's source cost 9 plus 9, 18, not an improvement. I can get to E in F's source cost 9 plus 5 for 14, not an improvement. It's equal to what we've already got, so there's no need to update it. We're going to leave that one alone. And lastly, I can get to G in 11. F's source cost of 9 plus 2 more. So I'll say this is 11 through F. All right. Next up is D, so we'll mark that as true. Find the things that D is adjacent to with its source cost of 10, right? No, I didn't say that right. Yeah. D's source cost of 10, right? The source cost of D is going from A to C to D. So then I've got to add 10 to anything that D can reach. D can only reach E, that's marked unknown so far. So this 10 plus 7 is a 17. That's not an improvement over this 14. So D doesn't get to update anything, right? Because this F is already marked as true. So D's other neighbor here and all of the other things D is connected to is marked as true. So that one's done. E gets me an update. Of course, E is not connected to anything that isn't already marked as true. So we'll just leave E there as well. G isn't connected to anything that isn't marked as true. So then I end up with my my Dijkstras table looking something like that. All of these items here are marked as true. I can see all of my parents to get back through my path. And then these are the weights from A to a particular vertex. So there's Dijkstras. Looks something like this. I can see the distances from A to each one of these vertices. It's 11 to get to G, 14 to get to E. And then these arrows show the previous path so I can figure out how I would actually connect those things. Algorithm families. We learned some algorithms early on, and then we started classifying them later. Here's a nice last viewing of an XKCD comic before the semester ends. This one gives us our traveling salesperson humor form. So, excuse me. Get some water here. We looked at 6 algorithm families, and we kind of put them in pairs because they had some similarities across those pair sets. So Brute force and greedy got put in there together. Brute force was a simple, straightforward way to do things. It was usually inefficient, but it was always optimal because it looked at every possible solution. So if you look at every possible solution and you keep track of them, you will eventually find the optimal solution. So brute force was always optimal, but it was usually always optimal in terms of finding the optimal solution. It wasn't optimal in terms of efficiency. It was usually fairly inefficient. Greedy ended up being a lot more efficient time-wise, but it lost this guaranteed optimal solution. Some greedy applications will give you something optimal, like the elementary sorts we looked at. Bubble sort, selection sort, insertion sort. Those are all greedy. Here's the thing. How can I fix this thing with respect to its neighbor? Once I do that, that's all I'm going to do. That's how bubble sort works. It's a greedy choice. Here's my locally optimal decision. 2 points. Are they in the right order? If they are, I'm going to leave it. If they're not, I'm going to fix it. So that was greedy. And in those cases, the three that I mentioned, selection sort, insertion sort, bubble sort, they were greedy and they were optimal. And we looked at making change with certain denominations and availability. A greedy algorithm would be optimal. With other denominations, it wasn't necessarily the case. Just like if we're using a greedy approach to climbing to the tallest point on Earth, I would probably get stuck somewhere at a local maximum. So greedy algorithms and brute force algorithms were similar in that they usually had a fairly lightweight way to find the answer. In the brute force, I'm just going to look at everything. And in greedy, it's like, I'm just going to take the best that I see. That's it. It's very simple. But without the ability to reconsider, sometimes greedy algorithms are not optimal. So we looked at some algorithms like the knapsack algorithm, that a greedy solution just couldn't get me anything good on it. But a modification of the problem, we said, what if we got fractional knapsack? Now I can cut an item into a portion and use that portions of the value from a shaved item. So that made the greedy approach optimal because it never made a choice that prevented us from making a better choice later down the road. The next pair of algorithm families that were similar were divide and conquer and dynamic programming. Both these two approaches looked at the big problem as a collection of smaller problems that were a similar problem. So in divide and conquer, we would take our big problem and divide it into two or more subproblems, and those subproblems were non-overlapping. So the very common one for divide and conquer is, of course, binary search. When I'm looking for an item in a sorted container, if I look in the middle, I don't find that item there, then the item I'm looking for is either before it or after it, but it can't be in both places. So then once I do that, I can say, well, let's just throw away the half that I know that it's not in, and I can repeat my search in a smaller area. And that's divide and conquer. A lot of those solutions are recursive. They're pretty straightforward. Dynamic programming, much more complicated. It took the same approach and said, we've got a big problem. It's going to be a lot easier to solve this if I've got a smaller version of that problem. However, this problem isn't as independent as, say, a binary search, because as I look at smaller versions of this problem and I start to grow my solution, a grown solution might use the same smaller version of the problem multiple times. So rather than using this smaller solution and calculating it multiple times, we're going to call that our overlapping subproblem. I'm going to reuse those values after I calculate them, and then that's going to make things faster. That brought us memoization and the shorthand of saying, hey, I'm going to put this in a memo. All right? So dynamic programming and divide and conquer, those both said, let's get smaller subproblems. Divide and conquer had non-overlapping subproblems, and DP has to have overlapping subproblems in order for it to work well. All right? The last two families, backtracking and branch and bound, are very closely related because branch and bound generally ends up looking like backtracking with additional constraints. Backtracking is something that works in an almost brute force fashion because we say that backtracking is going to systematically check all possible solutions. Wow, that is exactly what the definition of brute force is. However, backtracking also says if we do this in a structured manner, then when I find a bad solution or a bad partial solution, I can save myself a lot of time that a brute force solution wouldn't, right? So for instance, if I'm making change with brute force and I've got to pick between some subset of these 10 coins, and I give you 2 coins that has too much change already, in a brute force solution, I would continue to see what other combinations of the remaining 8 coins might or might not work, even though they would all fail because the initial 2 coins had broken the constraint. However, with backtracking, I say, well, if I start out by giving you these 2 coins, that violates a constraint. I don't even need to deal with the remaining 8 coins. I'm going to prune this bad solution, and I end up with something that still is that same asymptotic complexity of brute force. It says we're checking them all, but in practice it ends up much faster because as constraints get violated, then we stop looking at things. So, and it works out well when we've got a lot of constraints, because with a lot of constraints, we're more likely to violate a constraint. So we cut more and more out by pruning. Or when I don't have very many constraints at all, it's easy to just throw a solution out there that actually gets through the particular problem that we're working on without violating any constraints. So backtracking is fairly efficient. And even though it looks like asymptotically it's the same as brute force, in practice it is always much faster. Branch and bound is just like backtracking, but we also add the fact that once I know something about a solution and I'm trying to optimize a solution, backtracking wasn't really interested in optimizing. It just said, can I find a way to do this without violating a constraint? Branch and bound says we need to find a way to do this without violating a constraint, but not a way to do it. I need to find the way to do it. I need to find the most efficient way to do this. So branch and bound adds an additional constraint that it manages, not managed by the problem now. It manages this additional cost. So if I've found some cost and I'm optimizing, if this current investigation, even if it hasn't violated a constraint, if it looks like it's going to be too costly, then I'm going to prune that as well. So in branch and bound, I can go through there and find the absolute best solution, and I will get there because I've added an additional constraint, this cost constraint. One thing that's important to make sure that you understand going into the exam, we looked at branch and bound in Project 4 in a minimization problem. We were minimizing to get to the shortest traveling salesperson path. A branch and bound algorithm is an optimization algorithm. If you're trying to do something that's a maximization, like I'm trying to maximize the amount of things that I can stick into my knapsack, I can do that with a branch and bound. I just have to turn everything around. In a minimization, I've got an upper bound that ends up being my final solution. In a maximization, I've got a lower bound that ends up being my final solution. So those things get reversed there. In minimization, I've got an estimate, which is my lower bound. In a maximization, I've got an estimate, which is an upper bound. So go back and make sure that you can sort of pick a problem like knapsack and just name all of the important parts of the branch and bound algorithm. What is the upper bound? What is the lower bound? Can I guess long, or do my guesses have to be short? Which one of those work, right? So make sure you understand that as you are reviewing your algorithmic families. I mentioned before we are going to have a DP problem, so it's a great place to have a little bit more talking about DP. So make sure that as you try to study the DP problems that we've already done, you understand them. One really good thing that you can do is take all of the solutions that we've gone through and make sure that you can write both of them bottom up and top down. So this particular slide suggests writing two versions of Fibonacci, top down and bottom up. Those are pretty straightforward, and we've already got them on previous slides. It's not gonna give you confidence to do that. Try to take something like Knight Moves, which was a very clear bottom up solution, and then write that top down and see how the ordering of the subproblems is dictated by the top down solution, and see how you don't fill out the entire memo of levels that you don't need to. So understanding that is great. Question here says, here is Fibonacci. What's the best description of the family that describes this current implementation? All right. It's brute force. Looks like it's going to be divide and conquer because I take this fib and I call fib again. But you'll note that fib of n minus 1 and fib of n minus 2 are overlapping, so it's not divide and conquer. And since we're not storing anything and saving ourselves time later, this is not DP yet. So in reality, this is just brute force because we're doing all the work. All the work that possibly could be done, all the work that needs to be done. We're doing everything. This is a brute force solution. Here's my top-down solution in terms of DP. We see we made a couple of modifications here. Instead of just returning what we've computed, we're going to store what we computed into some memo and keep that for later. And then rather than calculating this thing, if I can look it up, I'm going to return it before I make my subsequent calls to Fibonacci again. So that's a top-down solution, which is pretty straightforward way to convert the simple recursive algorithm to something that's DP. The great thing about that simple conversion is you can take some complicated recursive function that you might not even understand, and if it's something that you can write a DP on, you can memoize that. You can memoize a recursive function that you don't understand very easily just by saying, well, before I return, store this value, and before I calculate, look this value up. So that's pretty good. Bottom up, here, of course, we're talking something that's iterative. We're talking loops. Top down, recursion, bottom up, iteration. So I've got this for loop that goes from my small up to my big, and I can calculate my Fibonacci values just by saving those two previous ones. Notes for the exam, of course, if you decide you want a helper function, you can write it. You can write it below. You don't have to worry about doing a declaration like a compiler would want you to do. If you need a helper function and you write a helper function, because we've given you the function signature at the top of the page and you have to write under that, you can't necessarily write the helper function above the function that it's helping. And that's okay. We understand that. If you need to declare a structure, feel free to do that below, above it, on the right. As long as it's clear and the staff can read it, we'll be able to grade it fairly well. Just make sure that it's legible, and if something needs a discussion, put the discussion there. If there's arrows that are needed, draw the arrows. Saves us all time in the end. We don't have to do regrades, and we don't have to do grade concerns. So let's make that legible and straightforward. Here we are wrapping this up. We started at the beginning of the semester with no starter files. We said, come to this Sunday, and we're going to teach you how to use your IDE, and we're not going to give you much for it. Now, at the end of the semester, we're much better at design. We can take some of these problems ahead of time, ask the question, and then say, let's put a good design forward on this. Let's use memory efficiently. Let's use a proper algorithm before we get writing, so that we don't have to end up getting done and finding out after I got it done, after I debugged it, now it's too slow or uses too much memory or both. Let's fix that, right? Better at implementing things by a long shot. Everyone always thinks that the projects in 281 get easier, and I don't think they do. Students just get better. We're better at testing and debugging, of course. Plenty of optimizing that we learned our way through. And this analysis bit that we learned how to analyze our code with complexity for memory and time is great to get you some comparisons between different design choices. It's pretty good. Oh, I got a traveling question here. It says, top-down DP solution, is it a problem that the unordered map is initialized each time the function recurses? Which unordered map are we talking about here? This one here, I think that's what we're talking about. Well, there's a keyword in there in line 2. That's static. That static variable in a function makes it so that it doesn't actually get reinitialized, right? The first time this function gets called, it uses the static one, and then the second time it uses the same one. So this is not a problem here, right? All right. So we're happy to say that you've made it this far. You have come a long way. Trying to figure out what's next. Almost all of the upper level courses are now available to you. There's a couple that still need another prereq or so, but this long list of them is there. We've got a new course that starts fall 20. That's EECS 440 now. This is the search engine course, as it was called. It's got some advanced C++ in it. You got to do some real object-oriented programming work there. This is going to be basically our departmental replacement for or substitute for something that looks like 381. 381 is gone. 440 is the new thing. So that is a good course to check out. Professor Hamilton teaches it. Great work there. You can learn some pretty cool stuff. The other things that we can do is, of course, every time we looked up some of these problems on Stack Overflow, I think half of the suggestions were, well, just use this boost library and you can do it in one line. But we didn't allow boost in 281. Now that you're out of 281, you can learn boost. You can start using those libraries written by others. You can decide when to borrow from boost or when to use something from the STL, or as in 440, sometimes it's better if you write your own. And so with very specific applications, the STL doesn't always end up being the greatest. So with generic all-purpose things, the STL is hard to beat, but now you're capable of moving into new libraries. So that is about where we leave you. We would like to say thank you. We know this has been a more trying semester than normal with all of our social distancing and everyone leaving campus and online office hours and online final exams. It is going to be a challenge as we get through this. Hopefully one day soon our lives will all return to something that looks normal and we'll be able to meet back up in Ann Arbor. So thanks for coming. Thanks for staying with us, and good luck on the final. Remember, as I suggested in the midterm, come in calm, cool, relaxed. Set yourself up. Be prepared to succeed. I know you will. Thanks, gang.